Alright, it's recording.
Okay, so since the constants don't change with respect to t or x, we're just going to plug in the case u of x equals 0, because he gave us a nice function for that. This is the equation we used to get this, well, that's a given relation. U of x equals 0, if we take t to equal 0, this entire term goes to 1, so we just have the relation n equals 1 to infinity c of n sine of x over L. Now what we're trying to determine is c of m for an arbitrary integer constant, for an arbitrary integer m. So what we do from here is we multiply both sides by c of m, or sine, you'll see. Multiply both sides by sine m pi x over L. And so we multiply the other side by sine, and now this of course goes into the sum pretty easily. X over L. Okay, now this will give us a useful thing because he's given us a special property of sines. So we integrate both sides from 0 to L. We integrate this side from 0 to L. Now because the integral factor gives rid of constants and works well with sums, this reduces to integral. Now, this is the wonderful linearity condition Jacobs talks about a lot. And we're almost done, because most of the terms in this sum go to 0 immediately. Because if n is not equal to m, the function is 0. We know that because he gave us that nice little note. So the only term that will remain is c of m, integral from 0 to L, sine of m pi x over L squared dx, which is the case when m is equal to m, n is equal to m. All the other cases go to 0 because of the rule. And this, he also gave us what it's equal to, which is L over 2. Now we're getting somewhere. So this expression up here is easy to rewrite. We can just rewrite it as g of x sine of m pi x over L. And then we just multiply by 2 over L to cancel both sides. And we're done. We've derived an integral formula for the given relation.